Hello everyone. It's really a pleasure to be back here. And this is the fourth seminar of the joint initiative between the Italian Association for Artificial Intelligence and the AISB Association from UK, which is represented by the president, Bertie Müller. It's our pleasure to have to introduce our guest today, which is Melanie Mitchell. She doesn't really need an introduction, but I will do very brief intro in any case. So Melanie Mitchell is a professor at Santa Fe Institute. Her current research focuses on conceptual abstraction and analogy making in AI. She was also one of the developers of the very famous copycat system. She's author and or editor of 6 books and numerous scholarly papers in the field of AI, cognitive science, and complex systems. So she's really a transdisciplinary scientist. Her book, Complexity, A Guided Tour, won the 2010 Phi Beta Kappa Science Book Award, and her 2019 book, Artificial Intelligence, A Guide for Thinking Humans, were shortlisted for the 2023 Cosmos Prize for Scientific Writing. I'll give the word to Bertie. She wants to welcome Melanie as well, and then I will leave the floor to Melanie. So thank you for being here, Melanie. And Bertie, stage is yours.
Yeah, thank you, Antonio, for the introduction, and it's great to be part of this series of seminars. I don't think there's anything else to say about Melanie. We all know her and her work, and I look forward very much to your talk today.
Thank you.
So without further ado, over to Melanie.
Thank you. Thank you so much for inviting me. I'm going to share my screen. Okay, let's see. Okay, I hope you can see this. So I'm going to be talking, is that okay? Can you see that?
Yes.
Okay, great. So I'm going to be talking about the challenge of understanding the world for AI systems. So this has been a question for a long time. Do AI systems actually understand the data that they process? Well, of course, that depends what you mean by understand, but we want to think about, do they understand it in any human-like way? Well, there's been many examples throughout the history of AI of errors made because of a lack of understanding. And it does matter because in many cases, AI understanding can affect the kinds of errors that it makes and how predictable they are for us humans. So just as a few examples of some interesting failures of understanding in AI systems, back in 1918, this paper was talking about systems that were doing very well on object recognition and images using the ImageNet data set. And these systems, these deep neural networks, were extremely good at recognizing things like school buses with 100% confidence. But if those objects were changed in some way that made them a little different from what had been seen in the training data, that is by rotating the object using some kind of Photoshop-like program, in this way, now the same neural network is 99% confident that this is a garbage truck, is 100% confident that this is a punching bag, and is 92% confident that this is a snowplow. So this really showed a kind of brittleness to the understanding of objects that seemed so strong when objects were similar to the kinds of things that had been seen in the training data, but failed remarkably when the distribution of the test images differed significantly from that in the training data. Another kind of misunderstanding or lack of understanding in these systems comes from situations that are again, outside the distribution of the training data. This person tweeted that his car, which was running Tesla self-driving software, kept slamming on the brakes in this area with no stop sign until he noticed that this billboard, which was some kind of advertisement with an officer holding up a stop sign, was being interpreted by the car as a stop sign in the real world. So this kind of lack of understanding of context can create lots of errors. And in fact, the most common accident involving self-driving cars is that they slam on the brakes unexpectedly and the human driver in back of them crashes into them. So that kind of unpredictable, unexpected behavior when the cars are perceiving some reason to stop that humans wouldn't perceive can cause a lot of accidents. And humorously, people have picked up on this. This is a scene from San Francisco where there's a lot of robo-taxis that can be fooled into stopping by just random people wearing stop sign t-shirts. Other kinds of misunderstanding come from machine learning when systems like deep neural networks are trained with many examples to do classification, for instance, of skin lesions to classify whether they're malignant or not. And so one neural network that was trained did extremely well on this particular benchmark. But when the authors sort of looked more closely at what the system was doing, they found that the algorithm appeared more likely to interpret images with rulers as malignant, because when the picture was malignant, these came from, pathologists who were looking at these images. When the lesion was malignant, the pathologist would be measuring its size. So the rulers are more likely to appear in those, which made the system associate rulers with malignancy. That's called a shortcut or shortcut learning in machine learning. It's a very common kind of error that can happen and prevents these systems from doing well outside of the kinds of benchmarks that they're trained and tested on. Other kinds of machine learning errors can come, for instance, in language, like a translation software. This sentence to Google Translate that I gave it just a couple of months ago, of course, it's always changing, but I said the legislator accidentally left a copy of the important bill he was writing in the taxi. And the word bill was translated into French using the wrong sense of the word bill. Facture means the kind of bill that your plumber would give you rather than the kind of bill a legislator would write. So this is, again, a lack of understanding of the context. And those kinds of translation errors can actually have a lot of real-world consequences. For instance, it was seen that US asylum cases from Afghanistan were being translated into English, and there were lots of mistakes that actually could endanger the cases. But now we're, of course, in the era of large language models, and many people claim that these systems have achieved a richer human-like understanding than these previous AI systems. And in fact, when I gave the same translation example to ChatGPT, it translated the word bill correctly. And I can even ask it, how did you know how to translate the word bill? It has many possible meanings. And it can explain to me in great detail, rather verbosely, why it knows that the word bill in this context refers to legislation and so on. So that really does seem like the system is understanding the sentences that it's given. The neural network pioneer, Terry Sinofsky, wrote this paper recently sort of talking about his new feelings about what is happening in the world of AI. He said it's like a space alien suddenly appeared that could communicate with us in an eerily human way. Of course, large language models are not human, but some aspects of their behavior appear to be intelligent, appear to understand our language and our world. But if it's not human intelligence, what is the nature of their intelligence? And of course, this is the question that all of us in AI are grappling with right now. How do we characterize the intelligence of these systems? And there's really quite a heated debate going on in the AI community, as many of you know, about this very question. So some people like Blaise Aguirre-Iarcus, who's a researcher at Google, wrote that these language models do very much understand a wide range of concepts, even though their understanding is informed purely by text. On the other side of the debate are people like Jake Browning, a philosopher, and Yann LeCun, head of AI at Meta, who say that system trained on language alone will never approximate human intelligence or human understanding, even if trained from now until the heat death of the universe. So these are the kind of extreme opposing views on this question. People like Ilya Sutskever, co-founder of OpenAI, went even further and on the understanding side and said what's happening when we train these networks to predict the next word in text. They learn what he calls a world model, which is a projection of the world. He says it's very poetically, it's learning about people, the human condition, their hopes, dreams, motivations, and the neural network is learning some kind of compressed, abstract, usable representation of that, which is what many of us would say that's what understanding is having this kind of world model in our minds. However, the question of whether these neural networks learn these world models from predicting next word in text is still an open question. This is a bold claim, but so far it's not supported by a lot of evidence. And in fact, Yann LeCun again says that in fact these systems do not have world models. They don't actually understand or reason using world models, but instead they perform a kind of what he called approximate retrieval, that is looking at patterns that they have memorized from their training data and retrieving those patterns to solve new problems that they're posed with. And he says there's a continuum between reasoning and approximate retrieval, and these LLMs are largely on the retrieval side. Rao Kambapati, who's another AI researcher on the side of this approximate retrieval, quoted, he made this kind of snarky definition of emergent abilities, the preferred euphemism for what your LLM does when saying approximate retrieval sounds too unsexy. So given this debate, how is it that we could actually evaluate understanding in large language models to sort of figure out to what extent they learn these sort of compressed abstract models of the world versus just retrieving memorized patterns from training data? Well, one way is just to look at their behavior, to kind of give them what you might call a Turing test, just like I did with that translation example. But the problem is that this is subject to what people have called the ELIZA effect, using this metaphor of the very early chatbot ELIZA. In the 1960s, people talked to ELIZA. It was a very primitive chatbot, but they projected intelligence onto it because it was able to communicate in natural language. And so every time that we humans converse with a chatbot, we are using its verbal fluency as evidence for intelligence and understanding, because we are projecting that onto anything that can communicate with us fluently in language. So that to do something more objective rather than subjective, perhaps we can test them on understanding benchmarks, which is something that, of course, many people have been doing for a long time. And in fact, back in April, in the journal Nature, it was reported that AI is beating humans at these basic understanding tasks. They gave this plot which shows for many different benchmarks. Here's the human performance scaled to 100%. And here's how these large language models have been doing, or AI systems in general have been doing over the years. And you can see that for most of the benchmarks, human baseline has been exceeded. And the benchmarks are things like image classification, visual common sense, reading comprehension, multitask language understanding, visual reasoning. Note the words understanding, comprehension, common sense. Those are the names of the benchmarks, okay? But the problem is that just because a benchmark is named visual common sense or reading comprehension doesn't necessarily mean that it is actually testing that general underlying ability. It's always possible that these AI systems can do well on these benchmarks and have done very well on these benchmarks without having the general underlying capacity that the benchmark is named for. Either the benchmark itself might, or something very similar might have been in the training data of the large language models, or they might be using the kinds of shortcuts, these statistical associations that might be very subtle, unlike the ruler and the skin lesion, which was very blatant kind of shortcut. There might be some very subtle associations in these questions in the benchmark that give a hint to the answer without requiring actual understanding. So we have these problems of data contamination. The benchmark is in the training data, shortcuts, or this notion of approximate retrieval, sort of instead of exact retrieval of the question and answer, we have approximate retrieval of something similar that the machine has seen in its training. So other approaches have tried to evaluate these systems directly on tasks that require abstraction and reasoning, that is the sort of hallmarks of understanding, to see if they are actually doing a more general abstract kind of understanding ability. So here, this paper, which came out last year, called Reasoning or Reciting, asked the same question. Are these systems actually doing abstract general reasoning, or are they doing something more like approximate retrieval from their training set? And what they did was they tested GPT-4 in this case on many different reasoning tasks. And the blue bar is the ability, the performance or the accuracy of GPT-4 on the original benchmark. But then these researchers changed the questions in the benchmark to ones that, while they require the same kind of reasoning ability, actually were less likely to be seen in the training data. They call these counterfactual tasks. So let me show you an example with code execution. So GPT-4 is very good at taking a little snippet of Python code and printing out what that code would do. So, you know, sorting a list like this, and does many other kinds of snippets of code. So that's this blue bar. And this is the kind of prompt that was given. Okay, what is the following code snippet in Python 3.7 print? But then they devised a counterfactual version of this task, which is a very simple change to Python. They say there's a new programming language called ThonPy, which is identical, except things like lists and tuples and strings use one-based indexing instead of zero-based indexing. So in Python, the first element of the list is indexed at 0, the second at 1, and so on. So they said, well, okay, let's just change that and pretend that Python uses one-based indexing. Now solve the problem. And you can see by this red bar that the ability of GPT-4 to do that was dramatically worse than its original ability on original Python, which it had been trained on. So the idea here is that a human programmer who understands Python could easily adapt to this kind of change. That's something that understanding allows you to do, is to adapt to kind of changes in the world that you haven't seen before by adapting your knowledge that you understand. But this system was unable to adapt, which makes it somewhat likely that it's using patterns from the training data, which consists of the original zero-based indexing in Python. And what these researchers said is, while current language models may possess abstract task-solving skills to a degree, they often rely on narrow, non-transferable, or generalizable procedures for task solving. And this same kind of thing has been shown in many other papers. This recent paper, Embers of Autoregression, showed that for many different tasks, they had a version that was common in the pre-training set and a version that was rare, but required the same kind of abstract reasoning. And you can see that GPT-4 here tends to do much worse on the rare version than the common version. And this paper from Apple, which came out quite recently, did the same kind of tests on mathematical reasoning and found these bars, which are the difference between models on the original benchmark, in which they did very well, and the modified benchmark, which just changed some of the names, the numbers, and added irrelevant information, produced a very dramatic decrease in accuracy. So I'll just give you one more example, which is something that my own group has worked on, which is analogical reasoning. So in 2023, this paper called Emergent Analogical Reasoning in Large Language Models came out from a group at UCLA. And what they showed is that in several benchmarks for analogical reasoning, GPT-3, in this case, had a zero-shot ability to do this kind of analogical reasoning. This got a lot of press, that GPT-3 was doing very well on making analogies better than undergrads in college. And here I'm going to talk about two of the domains they looked at, two of the benchmarks. One was a benchmark of letter string analogy problems, where you have one string changes to another string using some rule. You have to figure out what the rule is and apply it to a new string. So, here the D changed to the next letter in the alphabet. So here the L would change to the next letter in the alphabet. And they had several different types of these letter string problems, like remove the redundant letter, here fix the alphabetic sequence. And what they found is that GPT-3 was quite good at these kinds of problems without any special training. The same is true for a different domain, which they call digit matrix problems. So here, you're given a little matrix in which numbers have some kind of relationship across the rows and the columns, and you have to fill in the missing matrix entry. So it should be pretty obvious. This should be 6. Or here we have 2, 5, 6, 5, 6, 2, 6, 2. So it would be 5. This is a logical AND, where you AND the two first elements of a row to make the last element. Okay, so what they found is that on both the letter string analogies and the digit matrix problems, GPT-3 outperformed on average human undergrads on these problems. And their conclusion was that somehow through its pre-training, GPT-3 had an emergent ability for analogical reasoning. So my colleague Martha Lewis and I tested the robustness of this in a similar way to what I showed you before with testing the robustness of code execution in Python. So what we did was we said, well, if you're able to do those kinds of problems that were in the benchmarks that were tested by the original researchers, you should be able to similarly solve some simple variations. So one of our variations was you have an alphabet except some of the letters are shuffled, like here the M and the E are exchanged. Now use this alphabet instead of the original alphabet to solve a problem like this, where you might notice that MVGHI is almost a sequence in this alphabet, and it turns into a sequence MFGI. Do the same thing to FGLIJ. Okay, or we had another kind of variant where instead of letters, our alphabet consisted of symbols, in this order. And we gave people and machines little analogy problems using these symbols. So it's the same kind of problems, except using kind of different, a varied content for the problem. And we found that this is a plot of the accuracy, the average accuracy over different kinds of problems, ones which have 0 letters permuted in the alphabet, 2, 5, 10, 20, and alphabets that we use these symbols. And you can see that while humans stay relatively high in their accuracy, the different GPT models actually go down quite a bit, especially for these symbol alphabets, which are very different from anything they've seen in their training data. So humans are able to adapt much better than these GPT models. And we also did a variation on these digit matrix problems, a very simple variation where we just moved the blank element that was supposed to be filled in from the bottom right to a random position. So this absolutely did not affect humans. Here's the human accuracy on the original versus the human accuracy on the blank in an alternate position. They're essentially the same. Whereas the GPT models, here GPT 3.5 and GPT 4, both dropped very substantially in their accuracy. So these simple variations cause these systems to break, to not perform well. And so I would summarize the take-home message is that these large language models are often dramatically better on solving reasoning tasks that are similar to those seen in the training data, which reflects some failures of abstract understanding. So then there's this question, what do humans have here that allow them to be more robust than machines? And how can we get machines to learn and use these kinds of more robust human-like concepts and abstractions? Well, I'll first, in the last 10 minutes or so, I'll talk a little bit about what cognitive science has to say about concepts and abstractions, and then how a lot of people are thinking about trying to get machines to achieve this kind of flexibility and robustness. So human concepts are mental models of categories, situations, events, and even one's own self, an internal state. So consider the concept of something being on top of something else, okay? So we know that concepts act very compositionally in humans. If we understand the concept of one thing being on top of another thing, like this yellow block being on top of this blue block, we can then understand that this green block is on top of both of the blocks, and so on. If we understand the idea of, say, a cat on top of a television set, we can understand the concept of a television set on a cat. Much less likely, but here I got this DALL-E to draw this picture, cat on top of television. When I gave it television on top of cat, it was much harder to get it to actually draw something. Concepts have causal structure and enable predictions, reasoning, and common sense. So, even babies learn very early on about the causal structure of the world, how actions that they take in the world, especially for like things that are on top of other things, can cause certain effects. They understand how to, for instance, get themselves on top of something else, if they understand the spatial concept of on top of, and they can understand sort of topological relationships, like if you put your shoes on top of your socks, you have to put your socks on first. So kind of common sense knowledge. But also concepts can be flexibly abstracted to new situations via analogy and metaphor. So just keeping on with this on top of example, here are some metaphors in which on top of is used to mean something that's not necessarily physically spatial, but is adapted to a different domain, like on top of a social hierarchy. And we do this with all of our concepts. And it's one of the key ways in which we can adapt our concepts to new situations. So Larry Barsalou, a cognitive scientist who studied concepts, defined a concept as a competence or disposition for generating infinite conceptualizations of a category. Kind of a mouthful, but what he means is that concepts are generative models, and they can generate any number of conceptualizations of some category, like on top of, as I just showed you. And this is really our superpower in intelligence, is having such abilities for generating these and recognizing these different conceptualizations. Lakoff and Johnson and others famously proposed that all of our abstract concepts are learned via metaphors involving sort of basic physical experiences, really. So, for example, social interactions are understood in some ways via physical temperature. You know, she gave me a warm greeting, for example. We don't even notice that that's a metaphor because it seems so sort of intrinsic in language. Status is mapped onto physical location. She's 2 rungs above me on the corporate ladder. So Lakoff and Johnson have a book called Metaphors We Live By, in which they give many, many, many examples of this kind of thing. It's a really fascinating book, which I recommend. And Elizabeth Spelke, who's a developmental psychologist, has proposed that concept learning builds on what she thinks is an innate system of what she calls core knowledge. And core knowledge involves things like the notion that the world is divided into objects, basic ideas of numerosity, like greater than or less than or bigger than or smaller than, basic geometry and topology, like putting on your socks first and then your shoes, understanding geometric shapes and ideas of boundaries and other kinds of spatial concepts, and notions of agents and their goal-directed behavior versus non-goal-directed entities. So this is an old proposal in cognitive science. There's a lot of controversy about it, but it does get at the idea that there's certain kinds of knowledge that we either are born with or learn very early on, and we use that to build up our more abstract concepts. So Francois Chollet of Google, researcher at Google, took these ideas about concepts, some of the ideas about concepts, and developed what he called the abstraction and reasoning corpus, which tries to capture many of these kinds of ideas about how concepts should work. And it's a domain for very open-ended concept induction and abstract reasoning. So let me give you a couple of examples. So this is a little concept induction and reasoning task. The idea is you have these grids, and each grid location can have a different color. And one grid transforms into another grid using some abstract rule. Okay, and you can probably very quickly see what the rule is here, because we understand notions of objects, of lines that extend to boundaries. We understand the notion of same colors and different colors, and like taking a different color and using that color. So you can easily take the rule that you have induced here and apply it to a new test input. So this is like a little mini machine learning problem with three training examples and one test. But 3 training examples is typically way too few to train, say, a neural network, but it's enough to train a human who has a lot of prior knowledge about the world. And so what Cholet wanted to do is develop these idealized problems that require some kind of basic understanding of the world, and to test either humans or machines on these problems to see how well they understand sort of and can use concepts for reasoning. Here's another example from this ARC domain. This one is a little harder, and but if you stare at it for a little while, you'll see that this is about shape invariance, that certain shapes are colored in certain ways, even if that shape is a different size and orientation and uses fewer colors, colored squares. Like here, this sort of sideways U shape is the same shape as this upside down U shape, and so on. So Cholet created 1,000 tasks. He published 800 of them for people to look at and held out 200 as a hidden test set or private test set, and put this challenge on the Kaggle website, which is a platform for machine learning challenges, offered some prize money. This was in 2020. In the end, about 900 teams competed to submit programs that could be tested to solve these kinds of tasks that could be tested on the private test set. And in the end, the winning program got about 20% accuracy. I don't have time to tell you how it worked right now, but if you're interested, you can ask at the question time. It's been estimated that humans get about between 80 and 90%. So there's a big gap here. Now, 2024, there's a new version of this challenge called the ARC Prize, which is now offering a much bigger monetary prize, $600,000 for a program that will exceed this, essentially human level on the hidden test set. So that's a lot of money. And I think a lot of people are working on it now. And of course, things have there's been progress. This is the current leaderboard, where the best program is getting about 53% accuracy, but it's kind of a brute force approach using, they're using large language models and lots of sort of synthetic training data. I'm not sure how well it's going to generalize in the end. But our group has been looking at this, and we identified some problems with the original ARC tasks that we think make it so that perhaps we could do better on testing understanding. So many of them are sort of hard for humans. 85% means that there's at least 15% that people find too hard. And it doesn't systematically test understanding of concepts. Even if a machine can answer that shape invariance task correctly, it doesn't mean that it has understood the concept of shape invariance, because there might be shortcuts that it could use. So what we did, these are some of my collaborators on this project. We created what we called the ConceptARC benchmark, which uses the same sort of domain, but it tries to do a more systematic test of understanding. And the way that this works is we identify certain sort of core concepts, spatial and semantic, And we designed the tasks to be variations on this conceptual theme, so that if a machine does well on a whole lot of problems involving the concept of center, it's a lot less likely that it's using a shortcut and more likely that it's having a better job of understanding that concept. So just to give you an example, and we also tried to make them easier for humans than the original ARC problems. In this problem, you remove the bottom object. So you're sort of understanding the concept of top and bottom. Okay, and we tested this on humans, on the original Kaggle winning program, and on GPT-4 using both a visual representation and a text representation that just gave each grid as a set of numbers representing colors. Okay, and everybody got that one. But here's a new variation on top and bottom. This one, color the top row red. Everybody got that. But here's a new variation on top and bottom. In this one, a little more complex, but the idea is to remove the top and bottom objects. Humans got 100%, but the two programs got it wrong. So we could see that there's kind of a lack of robust understanding of this top and bottom concept. And we saw in general on each of our concepts had 30 variations, 30 different tasks testing it. Humans on average get about 90% on this whole benchmark. The original Kaggle program, which got 20% on the original, gets about 50% on ours. And the GPT versions do worse. They, of course, haven't been specifically designed like the Kaggle program to deal with ARC tasks. So we still see a big gap. So just to conclude, can AI understand the world? Well, I think in principle, yes, but right now it has, even though it's incredible, it has many failures of understanding, which make it untrustworthy. And to understand the world in a human-like way, we need human-like knowledge systems and concepts, these mental models that are built up via composition, analogy, metaphor, and causal structure. And a big question, I think, of particular interest to this audience is the question of whether AI systems can achieve this without embodiment or active interaction in the real world. And I think that's a very interesting and open question that's, remains to be seen. They've achieved quite a lot without embodiment, but how far can they go? I'll stop here and be happy to answer any questions.
Okay, so thank you very much. Thank you very much, Melanie. Great talk. Okay, in the meanwhile, that we will take some questions from the audience. So I will ask to Bertie and Luciano to start, and then we can make the first round.
Well, I'd be intrigued to find out really why you think that AI systems as they are now, kind of based on LLMs, why they should be able to understand the world or reason in a mathematical sense. I think the recent Apple paper shows quite nicely that once you change certain things in very simple grade school maths problems, there doesn't seem to be any understanding whatsoever. And that kind of aligns with the underlying statistical methods that are used in machine learning and these LLMs.
Well, okay, so I'm a little more willing to grant understanding as not an all or nothing idea and more on a continuum. So to say they understand nothing whatsoever, maybe, I don't know. But there certainly does seem to be lack of human-like understanding in these systems. A lot of people kind of push back on that Apple paper and some of these other papers by saying, well, you you have to come up with the right prompt. You have to, kind of give it some examples of reasoning, and you have to do various sort of engineering-like things. So that's a problem with current the current paradigm we're in. Is it's like, well, it's hard to prove a negative. It's hard to prove that they couldn't with the right, some set of prompting and chain of thought and what have you, solve these problems. But what I think that paper really showed is that when we see very successful performance on a benchmark, like we have, like GPT 4.0 can get 95% of some math benchmark correct, we should view that with skepticism. And accuracy, just giving accuracy on a benchmark is not enough. It does not test robustness. And robustness is the key of understanding. And that's something that, is an issue with human testing as well. That, people do well on some standardized test, and we assume that they understand, the things that they were tested on, but they can also game the tests in ways. So I think it's, we have to come up with better ways to evaluate these systems.
Yeah.
Okay, can I have a comment and a question for Melanie?
Mm-hmm.
Okay, so first of all, thank you for the very interesting presentation. Very nice. And I really appreciate all the arguments. So there are three words that resound very much in my mind, which is a generative, action, and embodiment. In the sense that it looks like, also in your presentations, that the generative aspect is really an important dimension of understanding. This is, I think, also, in your data set. So I suppose that you, in order to generate your data set, you have built like a generative model or pseudo like this, where actions are where every tripole of pictures are the results of applying some action to so it's not just a matter of finding relationship between patterns, but I think understanding means also being able to understand how you can operate on an object in order to modify it and obtain another object. And this goes also to interaction and embodiment, in the sense that we have a body and we know, human has the body defines the type of action that you can do and that you are able to do. And we are, I think, a lot biased. Our background knowledge is biased by these capacities. And we interpret the world also in terms of how we can interact with them. I don't know if you can comment on this.
Yeah, I think clearly we interpret the world and each other in terms of the things that we ourselves can do with our bodies, and we're very our intelligence is very embodied. You're right, and different kinds of species with different kinds of embodiment and environments obviously have a different kind of intelligence. So, I guess the question is, could something that's not embodied, that doesn't interact with the world, but can, is just sort of passively fed language, which sort of is an encoding of our intelligence, our thinking, our experiences, can it sort of get from that the equivalent of what we get from embodiment? I think that's probably unlikely, but I won't say it's definitely wrong. I'm surprised at how far these systems have gotten and what they can do just by, digesting all of the language of text generated by humanity in some sense. It's pretty astonishing. But I do think, that it's certainly not an efficient way to get there. It's taking up a huge amount of energy, and it's pretty unsustainable. But in principle, I'm not sure. But I think in practice, we're going to have to actually train our systems in a different way that is a more embodied way for them to learn about this kind of core knowledge that's going to enable them to be more robust.
Okay, so we have a number of questions via the chat. I will pick some of them. For example, one question is, does a universal core of common sense exist, or is common sense entirely shaped by cultural and individual factors? So this is more a question to the cognitive scientists, so to speak.
I would say that it's both. We all, at least for humans, we all share the same kind of bodies, and we share a lot of things, a lot of cognitive aspects so common sense, that we share a lot of things in common sense. But clearly some things are cultural and may vary between different cultures. So I would say it's really a matter of both. And I guess, I don't know, anyone else can chime in too.
Yeah, no. Other question, I mean, really I'm jumping here and there, but another question is about causal reasoning involving physical forces. So are there tests, meaning available data set benchmarks that go and test this kind of let's say LLMs on this kind of task? I guess so, but probably.
Yeah, I think there's several different such benchmarks. There's one I think called DynaBench. There's some benchmarks that have been put together by Josh Tannenbaum's group at MIT on trying to predict what's going to happen in some kind of simple physical situation. And this is something that also large language models are not yet at human level on, although it's somewhat surprising what they can do. I mean, one of the things we've seen certainly is that their visual reasoning abilities are certainly much worse than their text abilities to reason using text. And so linking up language and vision, doing these multimodal models that actually can do physical reasoning is still, I think, very open, and something that probably a lot of people are going to be working on over the next decade. But there's also, some debate about how much can be learned from, say, watching videos on YouTube about the physics of the world, and a lot of different claims about how that's going to turn out.
Yeah, indeed. I mean, with your answer, you also replied to another question about multimodality, and the question was about whether visual language model can actually improve, let's say, the performance of these systems by encoding this kind of multimodal knowledge. And I think your answer already went there. So
yeah, I mean, it's interesting that a lot of people thought, okay, these problems that large language models have will be solved once we sort of incorporate different modalities, because their concepts will be grounded in the world. But it actually didn't turn out to work that way. They have not been that much improved by multimodal training, and that's been a surprising thing to me.
Yeah. So, okay, I have another comment, and so we are in a sort of historic period, because for the first time since Herbert Simon, we had let's see, 2 Nobel Prizes that were given to AI scientists, to 3 AI scientists, okay, for their work on different levels of neural network architectures. So I think it is really, let's say, something huge that is that is happening right now with this kind of system, with this kind of model. So don't you think that most of the confusion that you have talked about during your talk is due to the fact that human level performances on some task or on integrated task are somehow, let's say, confounded with the idea of human-like computation that lead to to that kind of output? I think this looks like, from a quantity scientist point of view, a sort of let's say ascription fallacy. So if you just look at the behavioral performances of these systems, I mean, you cannot really say very much about the underlying competencies that have actually provided this output, even because we know that by design their internal mechanisms are very different with respect to, let's say, the corresponding mechanisms that we have in that lead, for example, other biological systems like us to the very same output. So I just want a comment from you on that.
Yeah, that's a great point, and it's certainly true. You know, they work very differently than we do. They learn very differently than we do. On the other hand, it kind of depends what level you're talking about. You know, so you can say, okay, a transformer is very unlike a human brain. It doesn't work the same way. It doesn't learn the same way. But you could still do something like Ilias Sutskever did by saying, well, there's an emergent model in these systems, an emergent world model that works similarly to the way human world models do in our brains. You know, I don't necessarily believe that, but it's kind of a different level of description. And a lot of people have tried to say that these systems at some level of description sort of are models of human cognition in some way. And it's, you know, some of the evidence is behavioral, some of the evidence is more dealing with kind of mechanistic interpretability results. But it's very, you know, it's controversial, as you say, because, you know, it's hard to say at what level is this really the case.
Yeah, great, thank you. I'm going towards other questions in the chat. There's another one that say, do you think we have to focus on the broad accuracy of AI across all benchmarks, or can we abstract the strongest accuracy as an understanding of concept? For example, disregarding symbol performance. I don't know. I was just reading the thing. I don't know whether.
Yeah, I'm not exactly sure where that's going, but I think accuracy alone is never a good measure of capability, just because there's so many reasons why you could be accurate on a particular benchmark without a deep understanding and a robust ability. So just because a machine passes the bar exam doesn't mean that it can go be a lawyer, probably similar to humans, but even more so for machines. Yeah. So I think that we have to go beyond accuracy as a measure and look more deeply at both behavior and internal mechanisms.
Great answer. There is another question concerning the idea of core concepts. So the idea, or the question is how this idea of core concept is connected somehow to the idea of having a sort of bottom-up, let's say, data feeding within this core knowledge and core concept. So what is the connection between these two aspects? Because on one hand, they looks like they are innate, so somehow wired in, top down, but on the other hand, how this data driven versus say other model are
right
connected.
So this is, you know, been a debate for a long time in cognitive science, to what extent are certain concepts innate versus learned. and what can be learned versus what has to be innate. So, one example is Chomsky's view of language, which says that in order to learn language, you have to have certain kinds of innate structures in your brain or your mind. And I think that's been disproven by language models, because they did not have those kinds of structures, and yet they were able to learn how to use language almost perfectly, given enough data. There's other ideas, the sort of what's been called rationalist versus empiricist debate, where the idea that we have certain basic concepts, like I mentioned, Spelke proposed with her ideas of objectness and agency and numerosity and all of that, and saying that those need to be innate, and we bootstrap. And off of those, there's been some evidence from developmental psych that is the case, other evidence that it's not the case, that these things maybe have to be learned. So I think it's all still kind of up in the air. And, psychology is not that old a field. It's only been really around as a scientific field for maybe 100 years or something. So it's not like physics. We haven't figured out, the basic laws of learning and of concepts. And so I think that we don't really know the answers to these questions yet. And I think that, doing research on AI and cognitive science at the same time, kind of in that area, is going to yield progress, not just on AI, but also on understanding our own cognition.
Okay, so I just want to really say thank you again to Melanie. We've been really happy to have you here, and thank you also to all the participants online. We had really many people online, many questions, and to Luciano Serafini, of course, and Bertie Müller from the Italian Association for Artificial Intelligence and from the AISB. And we look forward to learn more and about all these aspects that you have mentioned in your talk. And we will have another joint session in around, let's say, 1 month from here, and we will keep you posted. So thank you again, Melanie.
Thank you. It's been a great discussion. Thanks a lot to everyone who listened. Bye-bye.
Bye.